data for data-only attack generation. So a little bit about our team. We are systems security researchers from Pennsylvania State University. And our research interests include vulnerability detection, exploitation, and defense. Song Zhechang and I are PhD students, and Professor Honghu is our advisor. So, okay, let's start. So, control flow hijacking is a predominant approach to exploit memory bugs in past decades. So, in control flow hijacking, attackers first leverage a memory bug to get some memory access primitives like arbitrary read or write, and then leverage these memory access primitives to corrupt some control data like return address or function pointer, and which further can divert the control flow to achieve malicious goals like arbitrary code execution. So in past few years, attackers can build some attacks like code injection attacks or code reuse attacks. However, researchers have proposed many different solutions to prevent such attack. For example, code pointer integrity can protect the control data, and code control flow integrity can prevent abnormal control flow being executed. So nowadays, actually, it is difficult to hijack the control flow. But at the same time, data-only attack shows great potential to be the next generation exploit method. So unlike control flow hijacking highly relies on the control data, data-only attack only need to corrupt non-control data, but I can achieve similar malicious goals, like arbitrary code execution. So in previous works, there are some work like data-oriented programming and block-oriented programming shows that the data-only attack can be Turing complete and can achieved automatically. So data-only attack shows so powerful. Is such a thing even possible? Yes, it is. So let's start from a classic data-only attack, which need to corrupt the CGI bin configuration string in non-HTTPD server. So actually, the attack is pretty simple and straightforward. And here is an example to show how a normal CGI request works. So first, when the server in the server initialization, it will first load the CGI bin configuration from the configuration file. And here, the file is called, the CGI bin configuration is user local HTTPD CGI bin. So what is CGI bin? Actually, CGI bin is also known as a common gateway interface. So it's a standard for running the executables on the server side for data processing. And the CGI bin configuration is a string of a directory that contains all valid executables. So in this case, the client will send a post request and follows a string called CGI bin and the calculator. So when the server receives this request, it will first parse this string and get the first part, which is CGI bin. So it knows that this is a CGI request. So it will parse the later part to get the executable name. So in this example, the executable is calculator. So it will search the calculator in the preloaded CGI bin configuration. And if found, it will run the calculator for the client. So we can see in this case, the CGI bin configuration is pretty important because it can just decide which executable can be executed by the client. So what if the configuration gets corrupted? Actually, this is how the attack does. So in this attack, attackers first leverage a heap corruption override to overwrite the CGI bin to a /bin. And then it will still post a CGI bin request. In this case, it will try to run the shell and follows a command to remove or delete a file called the root private file. The server receives this request, identify this is the CGI bin request, and identify that the client wants to run the shell. It will search shell in the /bin directory instead of the preloaded one. and will give the shell permission to the client and delete the file. Actually, there are many other powerful data-only attacks. For example, like corrupting the argument of set EUID to get the root privilege in WFTPT server. And in Blackhat USA 14, Yang Yu proposed an attack which only need to crop one variable called safe mode, and it can turn on the God mode in the IE browser. So the God mode actually allows the unsafe ActiveX controls to run, and which equals to arbitrary code execution. And other attacks like bypass the EMET in Windows and bypass the control flow guard in Windows. So from previous example, we can see that unlike control flow hijacking that need to build a complex attacking chain like ROP to bypass the defense mechanisms, data-only attacks are really just simple and straightforward. So in most cases, attackers only need to corrupt one variable or sometimes even one bit, and the attack is done. So why data-only attack is so powerful, but it is still not as pervasive as control flow hijacking attack nowadays? So we think the most important reason is that the non-control data actually is not hard to identify. Is hard to identify. So the question now is, how can we automatically identify security critical non-control data, or critical data for short, to build the data-only attacks? First, spotting the critical data is challenging. So unlike control data have common low-level properties, for example, specific data type or memory locations, critical data are defined based on their high-level semantics. However, a general analysis to infer the high-level semantics is impractical, especially on the large applications. So in previous work, researchers try to manually inspect the code base to identify the critical data, which is tedious, require large human efforts, and not scalable. Flow stitch can identify the critical data with explicit source or sinks, like the argument of syscore. And Clearly can only identify critical data related to the error codes in Linux kernel. So our contribution. In this paper, we first identify an important category of critical data called syscore guard variables. And we designed the branch force to identify them. And we also assess their probability because in previous work, they just assume there is an arbitrary memory rate primitive, but we want to assess their probability to see whether these variables indeed can be corrupted. And we implemented a framework called Viper. We identified 34 unknown syscore guard variables from 13 programs. And we built 4 new data-only attacks on SQLite and V8. And we open source our tool. Let's start from a classic data-only attack, and also this is our motivating example. The code is for OpenSSH server to authenticate users. So we can see there is a flag called authenticated with default value 0. And there is a while loop to keep retrieving the usernames and passwords and verify them. And if the password is correct, it will break the loop, set authenticated to 1, and log in. However, actually there is a memory bug in the function packet read, which can provide a memory write primitive, and the attackers can then set the authenticated to 1. So in this case, even provide the wrong password, the attacker can still log in the server. So we consider the authenticated is the critical data here. And the question is how to identify the authenticated automatically. So we first check the previous data-only attacks and get 2 observations. First, most data-only attack relies on security-related syscalls. So in this example, once it breaks the loop to log in, the server will finally execute the execute for the attacker. The second is security-related syscalls are often guarded by security checks. actually in the form of syscall guard branch as a conditional branch here at line 11, the if statement. And we consider the variables in this branch is a syscall guard variable. So we implemented Viper to automatically identify syscall guard variables. So before going deeper, we want to know whether syscall guard variables really matter in data-only attacks. So we checked existing 17 data-only attacks and found that 11 variables are syscall guard variables, are syscall arguments, and all other 6 are syscall guard variables. However, it is still challenging to identify syscall guard variables. And the first challenge is how to identify the sole contribution of each variable. Symbolic execution can identify a complete path to trigger the syscall, but it cannot tell us which variables are more critical compared to others. And the second challenge is how to make the analysis efficient and scalable. Static analysis can help, but it has some limitations on handling the indirect calls and perform the interprocedural analysis. So to efficiently locate the syscall guard branches, we designed branch force. And the core idea is we flip every branch during the execution. We hook the syscalls to see whether there are new security-related syscalls get triggered. And if yes, we consider the flipped branch is a syscall guard branch. And for illustration here, we have a program and an input. We first run the program with the input, and we record all triggered branches and syscalls. And then we rerun the program with the same input. But this time, we will forcefully flip the first branch during the execution. And we also record all triggered syscalls. If there are new syscalls get triggered, we consider this branch is the syscall guard branch. So we flip every branch in the execution and get a bunch of syscall guard branches. Through the branch force, we can obtain a bunch of potential syscall guard branches. However, we don't know whether they can be really flipped in the real-world scenario. So that's why we want to investigate the variables in these branches. So actually, we perform the backward data flow analysis of each variable in these branches and generate the data flow graph to see for these syscall guard variables. In our assessment, we have 2 metrics. So the first metric is the memory location. We consider global variables are easier to be corrupted compared with the heap variable and the stack variable. And the second metric is the number of memory write instructions among the left span of the variable. So we assume that every memory write instruction could be abused. And therefore, if there are more memory write instructions among the left span, we consider it has a higher likelihood to corrupt them. And here is the workflow of Viper. So given a program and input, the branch forcer will first dry run the program to collect the triggered syscalls and the branches. And then it will flip every branch during the re-execution and identify potential syscalls. We only flip the unique branch triggered by new syscalls, and we use fork server to speed up the re-execution. After getting the branches, syscalls, and the input, we will feed them to the variable rater. Variable rater will first record the execution trace of this input on the LLVM IR level. And we will simulate the execution based on the recorded trace and perform the backward data flow analysis. And finally, Viper will report the syscall guard variables with a high probability. We evaluate Viper on 20 programs. Live programs with known data-only attacks like the OpenSSH, and 7 programs from FastBench, including the SQLite, and 4 other well-tested programs like JavaScript engine V8. So we realized that one important factor is we want a corpus to achieve higher coverage, because only when our input can achieve this trigger the branch, we have the chance to flip it during the dynamic execution. So this is quite similar to the fuzzing. So actually, we are first try to search the test cases in the source code repository. Like in SQLite, we found a bunch of great test cases. If we cannot find, we will search online to see whether they are ready to use corpus, like the fuzzbench data case. And if we cannot find from the previous two methods, we will fuzz the program with AFL++ to try to get a relatively robust corpus. We totally identified 36 Cisco guard variables from 14 programs. And this chart shows the Cisco distribution. 15 variables are related to onLink, which can delete or overwrite files. And 10 variables are related to execute, which can execute arbitrary code. And the others are like change mode, change owner, which will change the file permission, and change root, change dir, symlink, set groups, set REUIDs, and mprotect. And we also investigated the exploitability. So we first emulate the memory write primitive in GDB. So we want to see whether confirm that all 36 Cisco guard variables can indeed trigger a security-related syscalls. And then we conduct a CVE investigation. We search the historical vulnerabilities, and we confirm that for 16 variables, there is indeed there is a CVE that can provide the provide memory write primitive to corrupt them. And finally, we build 4 data-only attacks. Here is the time cost. So in most programs, Viper can finish analysis within 5 minutes. And we also compare Viper with FlowStitch, which is an exploit generation tool for data-only attacks. And we can see the time cost is at the same level, so we can combine Viper with other tools for the automatic exploit generation. Okay, so in the following talk, I will show 3 data-only attacks we built, and 2 on SQLite, 1 on V8. SQLite is the most widely deployed database engine used in Android, iOS, Chrome, Safari. And we use Viper to test the SQLite. Viper reports 7 Cisco guard variables in SQLite. And we built 3 new data-only attacks on the top 3 Cisco guard variables. So the first variable is called DuecDG open. And by set the DuecDG open to 1, we can achieve the arbitrary command execution. And we will show a demo later. And the second is called ztemp file, which can achieve arbitrary file deletion. And the last one is delete. It can also achieve the arbitrary file deletion. Okay, so a little bit background about our first attack. So when SQLite processed a query, it has multiple ways to present or handle the output result. It can print the result on the standard output, or it can also save the result to a file. However, more than that, sometimes you may want to edit the result before saving them into file systems. And no problem, SQLite also has this last feature. So you can edit it before saving. For example, with the .1 -e, SQLite will send the output to the system text editor. And with -x, it will send the output to a spreadsheet like Excel. So the red code shows how SQLite opens the system text editors within the function called output reset. And we can see there is an if statement will check the value of DuecDG open. As long as the value is not 0, it will move to forward the command string, which is based on the ztemp file, and call the system to run the command. So how Viper identify DuecDG open? the branch force flips the if statement and catches the execute. And the variable rater generates the data flow graph for the PDUX-DG-open and the ztemp file, and found that they're really they are highly corruptible. Here is the first graph of generated by the variable rater, which is the data flow graph for the DUX-DG-open. And we can see, although it is a stack variable, it has a really large number of memory write instructions. And we checked the code, found that DUX-DG-open is a variable stored on the stack of the main function, and it assigned value at the very beginning, but only used here. So we consider there is a large chance to corrupt it. And this is the data flow graph for the ztemp file. And we can see ztemp file is also stored on the stack of main function and has a long lifespan. So after identifying these two interesting critical data, we need to one memory bug to build our the attack. So through the CV investigation, we identified there is a type confusion bug proposed by Kun Yang at Blackhat USA 17. So with this bug, we can get the arbitrary write primitive, and it also shows that bypass ASLR is feasible. And here is the attack demo. We can see here is a POC. We first infer the address of DUX-DG-open and the other address user to create the bug, exploit the bug. And we first time we use the bug to set DUX-DG-open to 1. And we set the temp file to touch hello, which will generate the hello. And we store the payload to a file. And we can see currently there is no hello in the system. And we generate the payload, and we try to run it with the payload. First, as for better presentation, I will set up a breakpoint as if DUX-DG-open, the statement, and feed the payload. We can see currently the DUX-DG-open will be set to 1. And we continue, we can see here we form up the Z command, and we can see there is a touch hello, and we continue and check the file. We can see hello is generated. Actually, we can also spawn a shell as long as we crop the ztemp file, the string. And while in the first attack, ztemp file is only the syscall argument, so the main part is DUX-DG-open. But Viper also identified another use of ztemp file in the large SQLite database, code base. So as this code shows, there is another function called clear temp file. It will check the ztemp file value first. If it's not 0, it will call the shell delete file to delete the file. So we catch this by flip the if statement and catch the onLink get triggered. And in this case, both syscall guard variables and the syscall arguments are the temp file. So unlike the previous attack, we need to leverage the bug twice. In this attack, we only need to corrupt the temp file, and this is a one-shot exploit. And here is the example. Similarly, we refer the address of the temp file and other objects. And in this case, we only need to corrupt the temp file to hello, which is the file name, and save it to the payload. Save the payload to file also. And we can see currently there is a hello, and we generate the payload. And we try to run it. So actually, the clear temp file will be executed several times. So we first set a breakpoint as a bug. Yeah, and then we set a breakpoint as a clear temp file. And we continue. We can see here the ztemp file will be set to the hello. And we catch the syscall of onLink to see whether it is actually gets triggered. Yeah, and yes, it's triggered. And we can see the argument is also hello. So the hello should be deleted. And we check it and see hello is deleted. And the third attack is on the JavaScript engine V8. So V8 is used in many popular applications like Chrome, Edge, Opera, and Node.js. And it has a very large code base, more than 3 million lines of 3 million lines of code in the latest version. So Viper can also test the V8, and it shows that there are 2 potential syscall variables, and one is highly corruptible. So this variable is a global variable and with a very large number of memory writing instructions. And here is the code about this variable. The variable is called the enable OS system. So we can see only when its value is not 0, V8 can spawn a shell. And we use an old CVE to bypass ASLR first. And then we reuse the CVE to set the options enable OS system to 1 to get to run a shell and execute the arbitrary command. And here is the attack demo. We will first show the normal JavaScript file, which try to run the OS system with a shell. And we run it, we can see it is we are unable to run it. And the only way is run it with the option which called enable OS system. But for attackers, it is not possible because you need to rerun the server, the engine, and with a specific option, and which is too difficult for attackers. So we build our attack with fully ASLR. And here is our POC. We leverage the bug to bypass the ASLR and set the enable system to 1. And in this time, we rerun the V8. We can see we can run the shell. We can run the OS system even without setting the enable OS system option. And in summary, we implemented a Viper which can automatically spot in the syscall guard variables for data-only attacks. And we designed the branch force, and we also assess their capability. We found 34 previous unknown syscall guard variables and built 4 new data-only attacks on SQLite and V8. And we open source our tool and attacks. And thank you. I'm ready for questions.